Welcome to Noah Science, where Neptune, the dark distant giant, reveals hidden storms that defy expectation. Beyond the sun's fading reach, a blue world hangs still, while everything about it refuses stillness. Neptune seems serene from afar, yet that blue face conceals motion fierce enough to unsettle expectation. The farther the planet lies, the easier it becomes to mistake remoteness for weakness or quiet. Solar warmth cannot explain Neptune, because this dim giant still unleashes the solar system's fastest winds. Neptune is no hidden Saturn, but an ice giant shaped by different matter origins and rules. Its engine is internal, as Neptune releases stored heat that drives weather through the freezing dark. Even before storms appear, the planet's color is already a filter, not a simple surface truth. That deep blue is deceptive, masking layered chemistry, drifting hazes and structures the eye cannot read. Dark vortices and bright clouds keep changing, proving Neptune's storms live inside a restless, unstable system. A single Neptunian year outlasts generations, stretching seasons so widely that climate becomes almost beyond memory. To understand those skies, attention must fall downward from visible motion into depths pressure completely rewrites. Far below the clouds, pressure may force water, ammonia, and methane into unfamiliar planetary forms. Its magnetic field tilts wildly off-center, hinting that Neptune's deep interior is stranger than its face. Triton is not merely a moon, but evidence Neptune once captured chaos and reordered its system. For all our certainty, Neptune remains vivid, mostly because one brief flyby passed and kept going. That neglect matters because planets near Neptune's size appear common elsewhere, making this world cosmically important. Again and again, Neptune breaks easy explanations, forcing heat-wind chemistry and structure back into question. Its darkness is costly because distance and sparse data expose how limited planetary science still remains. Neptune ends not as emptiness, but as distant pressure, motion, hidden energy, and unfinished truth. Like, subscribe, and thank you for listening. Now enter Neptune's blue silence, where the unease begins. Neptune begins as a deception. From a distance, it looks orderly, even gentle, a deep blue world suspended at the dark rim of the solar system, so far from the sun that it seems as if almost nothing should happen there at all. The image invites the wrong conclusion. Blue suggests calm. Distance suggests stillness. Cold suggests silence. But Neptune is not the quiet ending of the planetary story. It is one of the places where that story becomes harder to read and more dangerous to simplify. What appears serene is a planet driven by hidden power, wrapped in an atmosphere that moves with startling speed, shaped by forces that do not announce themselves clearly from the outside. The familiar picture is smaller than the truth underneath. Neptune is not only remote, it is active and unresolved. That matters because remoteness encourages illusion. The farther a world sits from ordinary human experience, the easier it becomes to flatten it into a symbol. The last blue giant, the outer darkness, the cold frontier. Yet planets are not symbols. They are systems. And Neptune, despite its smooth color and apparently simple identity, is a system that refuses to behave like a frozen ornament at the edge of the sun's empire. It circles the sun at an average distance of about 4.5 billion kilometers so far away that sunlight there is drastically weaker than the light that floods Earth. Noon on Neptune does not resemble noon in the inner solar system. By ordinary intuition, a planet that far out should be dim, sluggish, nearly inert a place where the great engines of weather and change are winding down into cold obedience. Neptune does not obey that expectation. It preserves motion where stillness seems more logical. It keeps drama in a region of space that looks at first glance as if drama should be over. Even its discovery carries the mark of hidden forces. Neptune is not first found simply by seeing an obvious wanderer as ancient observers do with Mercury, Venus, Mars, Jupiter, and Saturn. It is discovered because something unseen is tugging on Uranus. Before Neptune is ever properly seen, it is inferred. Before it becomes an image, it is a problem. That origin matters. Neptune enters modern astronomy not as a bright certainty, but as a concealed cause, a world announced by the way it alters the behavior of something else. In other words, Neptune's story begins with the failure of the easy explanation. The known system does not fully work. Something beyond it is exerting pressure. Something darker and farther away is already shaping the whole. When observers finally locate Neptune in 1846, the achievement is extraordinary, but the deeper consequence is larger than the triumph itself. The solar system becomes stranger. The frontier is not empty. There are still massive worlds in the dark bodies whose presence is easier to detect through consequence than appearance. That pattern never truly leaves Neptune. Even now, the planet remains easier to summarize than to understand. It is classified, described, illustrated, and compared. Yet much of what makes it compelling lies beneath the labels. Neptune is the 8th planet from the Sun. Neptune is an ice giant. Neptune is slightly smaller than Uranus, but more massive. Neptune is rich in hydrogen, helium, and methane. All of this is true. None of it is enough. Facts alone do not reveal the force of a world. They do not tell you why its atmosphere can erupt into motions that seem to contradict the weakness of the sunlight reaching it. The real problem is not that Neptune lacks description. It is that description can create a false sense of completion. Once a world has a name, a color, a category, and a few statistics attached to it, the mind begins to feel that the work is mostly done. Neptune punishes that habit. Its blue appearance seems instantly legible, but appearance here is a filter, not a confession. Its great distance seems like the central fact, but distance is only the stage on which deeper processes become harder to detect. Its coldness seems like the governing truth, but cold planets are not necessarily dead planets. The farther one goes into Neptune's reality, the less it behaves like the outermost version of a familiar world, and the more it becomes its own kind of planetary argument. That argument begins with scale. Neptune is not a rocky sphere like Earth enlarged into grandeur. It is a giant world roughly 4 times Earth's diameter and more than 17 times Earth's mass, wrapped in thick layers of volatile material and atmosphere with no solid surface on which an observer could stand in any ordinary terrestrial sense. To descend into Neptune is not to approach stable ground hidden under clouds. It is to enter a deepening regime of pressure chemistry, compression, and heat, where earthly categories begin to thin out. The planet's visible face is only the outer skin of a much larger structure. And that is where the first real tension takes hold. Neptune looks simple because we mostly see its skin. We call it distant because distance is what we can measure most easily. We call it cold because the sunlight is weak. But the system beneath that skin is already preparing the contradiction that defines the planet. Neptune is not calm because it is cold. It is not quiet because it is far. It is not inactive because it is dim. The blue silence is an illusion produced by scale and distance. Under that beautiful color, the atmosphere is already moving. Under that motion, energy is being stored, released, and redistributed in ways that should not feel so powerful so far from the sun. And once that becomes visible, the planet changes meaning. Neptune stops being the decorative final giant in the schoolbook lineup and becomes something much more unsettling. A world whose violence survives, where intuition says it should fade. That is the first fracture in the easy story. The next is harder to ignore, because once the illusion of stillness breaks, another question follows immediately. If Neptune is so dark, so cold, and so far away, then what in this remote atmosphere is driving winds fast enough to outrun the expectations of an ordinary planet? Neptune should be too weakly lit to behave this violently. That is the paradox that changes the entire planet. By the time sunlight reaches Neptune, it has fallen to a tiny fraction of the intensity received by Earth. So little that the outer atmosphere ought to be running on a thin budget of solar energy. And yet, Neptune produces some of the fastest winds, measured anywhere in the solar system, with atmospheric flows that can reach well over 1,000 kilometers per hour, and in some regions push beyond 2,000. These are not minor breezes exaggerated by distance. They are planet-scale currents tearing through a world that by ordinary expectation should be sluggish with cold. The obvious explanation is sunshine. On Earth, the sun heats the surface unevenly. Pressure gradients form, warm air rises, cool air sinks, and weather begins. That model is not wrong. It is just incomplete. At Neptune, it becomes dramatically incomplete. Solar input still matters, because no atmosphere is entirely free from the star it orbits. But sunlight alone is nowhere near enough to explain the scale, persistence, and speed of what is happening. The real engine lies deeper. Neptune is cold on top, but it is not cold all the way down. The planet radiates significantly more energy into space than it receives from the sun, which means the atmosphere is not merely reacting to weak external light. It is being fed from below by stored planetary heat. This is the first major correction. Neptune's weather is not just weather. It is the visible behavior of an energy imbalance. Something inside the planet is still active enough to power motion on a global scale. That alone would be remarkable. But the real tension is sharper than that, because internal heat does not automatically produce supersonic winds in any neat or guaranteed way. It provides energy. Yes, but energy has to move through structure, pressure, rotation, chemistry, and layered atmospheric dynamics before it becomes a visible storm or a racing current. The answer seems clear until the system becomes visible. Neptune spins quickly, completing a rotation in about 16 hours, and fast rotation changes everything. It helps organize atmospheric motion into bands, jets, vortices, and long-lived circulation patterns. It turns rising and sinking flows into broader structures shaped by planetary scale. But rotation is not the whole answer either, because other giant planets spin rapidly, and yet Neptune still manages to be extreme in a way that unsettles neat comparison. Jupiter is larger. Saturn is more obviously banded. Uranus is also an ice giant. Still, Neptune, darker and farther out, keeps producing the kind of wind speeds that make the calm blue disk feel almost dishonest. This only looks simple from a distance. The atmosphere of Neptune is made mostly of hydrogen and helium, with methane contributing both chemistry and appearance. Methane absorbs red wavelengths of sunlight and helps give the planet its blue color. But color here is only the surface clue. The upper atmosphere contains hazes and clouds, while deeper levels likely involve more complicated mixtures under increasing pressure and temperature. Within this layered system, heat moving upward from the interior can create convection, and convection can interact with rotation to build large-scale circulation. Bright methane ice clouds sometimes appear high in the atmosphere, marking places where material rises and cools enough for condensation. Dark vortices can emerge like gigantic atmospheric wounds, anticyclonic systems that drift through the planet's blue face before fading from view. These are not random decorations. They are signs that Neptune's atmosphere is restless at many levels at once. What matters is not the cloud itself, but the machinery beneath it. And that machinery is difficult to isolate, because Neptune is so far away that even strong observations are thin slices of a much larger process. The Voyager 2 flyby in 1989 gives humanity its only close look at Neptune, and what it finds is not the quiet giant many might have expected. It reveals the Great Dark Spot, a massive storm system reminiscent in broad visual terms of Jupiter's famous Red One, along with bright companion clouds that suggest dynamic vertical motion in the surrounding atmosphere. But unlike Jupiter's Great Red Spot, Neptune's dark storms do not present themselves as easy, permanent landmarks. Later observations show that such features can disappear, while new dark spots can form elsewhere. Neptune's atmosphere does not merely endure, it rearranges itself. That instability is part of what makes the planet so scientifically difficult. A system that changes rapidly is harder to reduce to a tidy model, especially when the observer is billions of kilometers away and working with a tiny dataset spread across decades. Even the phrase supersonic winds needs care because it tempts the mind toward a simple spectacle when the deeper issue is more subtle. The atmosphere is not behaving like a single giant blast of air crossing a hard planetary surface. Wind speeds on Neptune are measured relative to the atmosphere and inferred through cloud tracking and spectral analysis. So what matters scientifically is not just that the numbers are large, but that such velocities emerge in a stratified, rotating, internally heated world where the expected solar driver is weak. Neptune keeps showing that the outer solar system is not the place where complexity fades. It is one of the places where complexity hides behind poor intuition. The farther from the sun, the easier it is to assume the engine must be winding down. Neptune answers with speed. It answers with dark storms, high clouds, deep circulation, and unexplained efficiency in turning hidden energy into motion. That is why the winds matter so much. They are not just a dramatic detail. They are the first unmistakable proof that Neptune's remoteness is not emptiness. Distance has not removed weather from the planet. It has made the weather harder to explain. And once a world begins to move this fast in near darkness, another simplification collapses with it. Neptune is not merely a smaller version of the gas giants people already think they understand. Its composition, its structure, and even the category used to describe it point toward a different planetary logic altogether. Neptune is often placed in the wrong family, and that mistake makes the planet seem easier than it is. In ordinary conversation, the giant planets are grouped together automatically, as if Jupiter, Saturn, Uranus, and Neptune were variations on a single theme. Large outer worlds made mostly of gas colder than Earth, scaled-up versions of one planetary design. The grouping is useful at a distance, but distance is exactly where Neptune becomes misleading. The obvious explanation is that Neptune is simply a smaller gas giant, a dimmer cousin of Jupiter and Saturn, built by the same rules and differing mainly in scale. The real problem is that this collapses an important distinction. Neptune is not just less of Jupiter. It belongs with Uranus to the category of ice giant, and that term points toward a different balance of materials, a different interior structure, and likely a different story of planetary formation. This matters because categories in astronomy are not only labels. They are compressed arguments about how a world exists. If the label is too broad, the explanation becomes shallow. Jupiter and Saturn are dominated by hydrogen and helium to an overwhelming degree. They are immense, deep envelope worlds whose great size allows them to hold onto the lightest and most abundant gases available in the young solar system. Neptune also has hydrogen and helium in its atmosphere, but proportionally, it contains far more of what planetary scientists call volatile substances, such as water ammonia and methane materials, that in the outer solar system condense more readily than hydrogen and helium, and that under planetary pressures no longer resemble familiar terrestrial forms. The word ice is therefore both helpful and deceptive. It does not mean Neptune is packed with literal frozen slabs stacked inside a dark blue shell. It means the planet likely contains a much larger fraction of these heavier compounds than Jupiter and Saturn do, mixed, compressed, heated, and transformed into exotic fluids and layers under enormous pressure. In other words, the difference is not cosmetic, it is structural. Neptune's mass is a little over 17 times that of Earth, while its radius is about 4 times Earth's. That makes it large giant by any terrestrial standard, but still far smaller than Jupiter, which outweighs it many times over. Yet Neptune is denser than Saturn, and not dramatically behind Jupiter in bulk density, which immediately tells you this is not simply a puffier version of the same thing. More of Neptune's mass is tied up in heavier material. More of its story lies beneath the cloud tops. This is why Neptune matters so much beyond itself. If one thinks only in terms of the old public picture of planets, Neptune is the elegant outer blue giant, almost decorative in its remoteness. But if one follows the composition seriously, Neptune becomes evidence that giant planets do not come in one simple form. Some pathways produce hydrogen-helium behemoths, like Jupiter. Others produce smaller but still massive planets, enriched in volatiles and burdened with deeper, stranger interiors. That difference matters not only inside our solar system, but for understanding planets around other stars. In the exoplanet era, worlds in the rough size range of Neptune appear to be common, perhaps more common than Jupiter-like planets in many observed systems. Which means Neptune is not a peripheral oddity. It may represent one of the galaxy's most important planetary types. The giant at the edge of our own system may actually be one of the templates for worlds elsewhere. And yet, the more representative a planet becomes, the more embarrassing our ignorance looks. Because Neptune is far away, difficult to observe and visited closely, only once it remains one of the least directly understood major planets, even while serving as a key to interpreting countless distant ones. The story on the surface is classification. The story underneath is that planetary science may rely on Neptune-like worlds more than the public imagination ever has. The category ice giant also carries a historical implication. Neptune and Uranus probably form under conditions that do not simply scale from Jupiter and Saturn. In the early solar system, growing a giant planet is a race against time. The disk of gas surrounding the young sun does not last forever. Cores have to form accrete material and in some cases capture thick gaseous envelopes before that primordial gas disperses. Jupiter and Saturn seem to win that race on a grand scale. Neptune does not. It becomes giant, but not giant enough to drown itself almost entirely in hydrogen and helium. That may reflect where it forms, how quickly it grows, whether it migrates, and how the young solar system shuffles mass and orbits during its violent early evolution. Neptune, then, is not merely a finished planet. It is a record of a timing problem. It is large enough to hold onto a vast atmosphere, but not so large that the deeper composition disappears behind a single, overwhelming envelope of light gases. It occupies a middle ground, and middle grounds in planetary science are often where the most instructive complications live. Even Neptune's appearance participates in this confusion. The public sees blue and thinks of atmosphere first. But Neptune's blue is produced mainly because methane in the upper atmosphere absorbs red light. That visual identity is real yet incomplete. The stronger blue of Neptune compared with Uranus hints that additional processes may be involved, perhaps related to haze properties, atmospheric chemistry, or vertical structure that are still being refined. Neptune keeps resisting the lazy summary. Its composition is deeper than its color. Its category is deeper than its silhouette. Its importance is larger than its place in the textbook order of planets. Neptune is not a spare gas giant left over at the edge. It is a heavier, richer, more chemically burdened kind of giant one that stores evidence of how planets form under constraint and how interiors become stranger as pressure rises. And once that distinction becomes clear, a deeper question follows. If Neptune is built differently from Jupiter and Saturn, if more of its mass lies in these compressed volatile layers and heavier materials, then what exactly is happening inside that hidden structure that allows the planet to keep giving off so much energy of its own long after the young solar system is gone? Neptune is cold enough to look extinguished, yet it is still leaking power into space. That is the contradiction that makes the planet more than a distant weather spectacle. Measurements show that Neptune radiates significantly more energy than it receives from the Sun, which means the world is not merely illuminated from the outside and then fading obediently into darkness. It is still releasing internal heat. The easy explanation is that all giant planets do this, and that Neptune is simply following the rule. The deeper truth is that Neptune does it in a way that remains scientifically uncomfortable because its energy budget is not just a background detail. It is one of the keys to the planet's violence and one of the clearest signs that something important inside the world is still active long after its formation. A planet so far from the Sun ought to be dominated by scarcity. Light is weak. Surface temperatures near the cloud tops are brutally low. The outer atmosphere should seem like the final thin shell of a world that has spent billions of years surrendering its warmth. But Neptune does not look thermally defeated. It emits more than double the energy it absorbs from sunlight, and that fact changes the frame completely. Neptune is not simply cold. It is cold on top and active below. It is not merely preserving ancient heat in silence. It is turning stored energy into visible atmospheric consequence. The real problem is not whether Neptune has an internal heat source. It clearly does. The real problem is why that source remains so effective and why Neptune appears more willing than nearby Uranus to let that buried energy escape. That comparison is where the mystery sharpens. Uranus and Neptune are similar in broad planetary class. They are often treated almost as twins, two ice giants pushed into the outer system, similar in size, similar in general composition, similar in public imagination. Yet, Uranus radiates only slightly more energy than it receives from the Sun, while Neptune radiates far more. The apparent siblings do not behave like siblings in thermal terms. That means the answer cannot be a lazy appeal to category. Something in Neptune's interior structure or history allows heat to move outward far more effectively. The obvious explanation is leftover formation heat. That is probably part of the story. Giant planets form through accretion, collision, compression, and gravitational collapse, and those processes store enormous amounts of energy deep inside the finished world. Over time, a planet can slowly release that energy into space. Neptune almost certainly carries such a reservoir. But the phrase leftover heat can sound more complete than it really is. Heat does not simply exist. It has to travel. It has to pass through layers of matter under huge pressure. It has to survive structures that can either encourage convection or suppress it. It has to move through a planet whose interior may be chemically stratified, dynamically complicated, and unlike any familiar environment on Earth. In other words, the energy source is only half the story. The pathway matters just as much. Planetary scientists have proposed several ways to think about Neptune's thermal behavior. One possibility is that Neptune's interior mixes more efficiently than Uranus does, allowing heat from deep layers to rise upward through convection and eventually affect the atmosphere. Another is that Uranus may contain stronger stable layers that trap heat below, while Neptune is less internally inhibited. There are also suggestions that composition gradients, phase transitions, and deep fluid dynamics in these volatile, rich interiors may affect how readily energy can escape. This is where the word ice giant stops sounding tidy and starts becoming difficult. Under the pressures inside Neptune, water, ammonia, and methane are not behaving like familiar household substances. They are compressed into hot, dense, electrically active states, forming deep fluid regions whose behavior is still being modeled rather than directly observed. Neptune is in part a planet-sized experiment running beyond our reach. Even some of the more dramatic ideas, like the possible formation and sinking of carbon-rich material into diamond-like phases at great depth, are not introduced, because science needs fantasy to stay interesting. They are introduced because under such pressures and temperatures, matter itself begins to reorganize in ways that may contribute to internal structure and heat transport. What matters is not any single speculative image. What matters is that Neptune's interior is not a simple reservoir with a faucet. It is a layered, pressured, evolving system where chemistry, density, and motion likely work together to determine how much ancient energy can still reach the upper world. And that upper world is where the hidden heat becomes visible without ever becoming obvious. Neptune does not glow to the human eye as a furnace. It translates internal power into circulation, cloud formation, storm growth, and planetary scale wind. Heat moving upward helps drive convection. Convection interacts with rotation. Rotation helps organize currents and jets. The atmosphere becomes the handwriting of the interior. But like any difficult handwriting, it is easy to misread. A bright cloud is not the heat source. A dark vortex is not the cause. These are consequences, surface expressions of energy moving through a system too deep for direct inspection. Neptune, then, is not only a weather planet. It is a thermal puzzle whose atmosphere acts as both evidence and disguise. The planet shows that energy is coming out, but it does not show cleanly how. That is why its heat matters so much narratively and scientifically. It turns Neptune from a distant object into an argument about planetary interiors, about how worlds store the memory of their birth, and about how similar-looking planets can diverge profoundly in hidden behavior. The achievement of describing Neptune as a cold blue giant is real. The cost of stopping there is larger. Because once internal heat enters the story, the planet's appearance can no longer be trusted as a full account of its nature. The smooth blue disk is not the face of simplicity. It is the mask worn by a layered atmosphere, filtering sunlight haze chemistry and rising energy into something the eye mistakes for coherence. And that means the next deeper question is no longer just why Neptune remains warm within. It is how that buried complexity gets turned into the color clouds and shifting visible skin that make the planet look so deceptively simple in the first place. Neptune looks simpler than it is because color is one of the most persuasive lies in planetary science. A blue world feels instantly legible. The mind sees the deep cobalt disk and reaches for an easy story-cold atmosphere, methane tint outer solar system calm. The image is so elegant that it seems to explain itself. But Neptune's color is not a confession. It is a filter. What the eye receives is not the planet in any complete sense, but sunlight altered by gases. Hazes, cloud layers, scattering effects, and the geometry of an atmosphere whose deeper workings remain partly hidden. The obvious explanation is methane. Methane in Neptune's atmosphere absorbs red wavelengths of sunlight and allows more blue light to be reflected back into space, which is why the planet does in fact appear blue. That part is real. But the real problem is that methane alone does not finish the job. It tells you something important, but not enough. Neptune is not blue in the simple, singular way a painted object is blue. Its visible face is the result of a layered optical process happening inside a thick atmosphere with vertical structure, changing clouds, photochemical hazes, and chemistry that responds to both incoming sunlight and rising internal energy. In other words, the planet's color is not a surface property, it is an atmospheric outcome. That distinction matters because once color becomes an outcome rather than a trait, the whole world starts to look less stable. Neptune's upper atmosphere contains hydrogen and helium as dominant components, with methane present in smaller but optically powerful quantities. High above deeper layers, sunlight interacts with this mixture, and the atmosphere sorts, absorbs, and scatters different wavelengths unevenly. But even this is only the beginning. Ultraviolet light from the sun can trigger photochemical reactions in the upper atmosphere, helping to form haze particles from methane and related compounds. These hazes do not simply sit above the planet like a neutral veil. They alter the way light moves through the atmosphere. They shape contrast. They mute or emphasize layers below. They participate in the visual identity of the entire world. Neptune, therefore, does not merely wear a color, it manufactures one. And manufacturing is not the same thing as revealing. The story on the surface is blue. The story underneath is atmospheric selection. This becomes even more revealing when Neptune is compared with Uranus. At first glance, the two planets seem visually related, both blue, both distant, both ice giants, wrapped in methane-bearing atmospheres. Yet Neptune appears as a deeper, richer blue than Uranus, and that difference has forced a more careful question. If methane is present in both atmospheres, why does Neptune look more saturated, more vivid, more intense? The answer seems clear until comparison makes it unstable. Researchers have proposed that differences in haze structure, particle behavior, and vertical atmospheric mixing may help explain the contrast. One current line of interpretation suggests that a haze layer common to both planets may be modified differently because Neptune's atmosphere is more dynamically active. Stronger vertical mixing could transport methane ice particles downward, clearing or reshaping the upper haze and allowing the planet's deeper blue appearance to emerge more forcefully. Uranus, quieter in some respects, may preserve haze in a way that softens or pales its visible tone. If that picture is broadly correct, then Neptune's color is not just chemistry. It is weather written in light. It is motion translated into appearance. It is the visible result of a planet whose atmosphere does not leave its own upper layers alone. That is a much stranger proposition than the public image usually allows. It means the very first thing human eyes notice about Neptune may already be evidence of dynamism. The color that suggests stillness may in fact be one of the signs that stillness is false. And beneath those broad optical effects, the planet's atmosphere keeps generating more complicated visual clues. Bright clouds appear and disappear, often at high altitudes, where methane can condense into ice crystals. These clouds can be startlingly luminous against the dark blue background, like brief exposed nerves in an otherwise smooth planetary body. Some form in bands, some cluster near storms, some erupt in places where vertical motions seem especially strong material, rising, cooling, condensing, then being torn along by powerful winds. Their brightness makes them easy to romanticize, but the deeper truth is harsher. They are atmospheric witnesses, not ornaments. They mark instability. They suggest upward transport. They hint that hidden energy is finding routes toward visibility. And visibility on Neptune is always selective. We do not see a solid surface. We do not see the full depth of the atmosphere. We do not see the boundary where familiar gas gives way to deeper compressed fluid regions. What we see is a shifting skin, whose appearance depends on what light can escape, what clouds happen to form, what haze layers happen to obscure, and what storms happen to disturb the order temporarily enough for deeper processes to announce themselves. Neptune is blue, yes. But blue is the smallest possible summary of a much larger atmospheric negotiation. The same is true of the planet's apparent smoothness. Images can make Neptune look almost polished, a serene disk with subtle banding and occasional dramatic features. That visual coherence is misleading. The atmosphere is not neatly arranged in the way a casual glance suggests. It is stratified, active, and periodically violent. Optical calm is not dynamic calm. A world can look smooth from billions of kilometers away and still be running fierce circulation beneath the layers of reflected light. Neptune's beauty therefore carries a scientific cost. The more aesthetically complete the image feels, the easier it becomes to stop asking what has been hidden to produce it. But on Neptune, the hidden part is almost always the decisive one. Color conceals depth. Haze conceals structure. Clouds reveal motion only in fragments. The planet's face is real, but it is not transparent. It is a screen built by chemistry, sunlight, and atmospheric architecture, and like any screen, it both shows and withholds. That is why Neptune remains so compelling. It offers an image of clarity while operating through obscurity. The blue disk seems unified, yet its visible character depends on layers that shift, react, and sometimes break open under strain. And when those layers do break open, the illusion of simplicity does not merely weaken. It fragments into something harder to predict, because the next thing the atmosphere reveals is not stable order, but storms that form, migrate, and vanish inside a system that still refuses to rest. Neptune does not merely have storms. It has storms that undermine the comforting fantasy that a planet can be understood once its major features are named. The first close images make this world look as though it is finally giving up one of its secrets. There on the blue disk, is a giant dark system, large enough to command attention. A planetary wound broad enough to earn a title. A visible sign that Neptune's weather can organize itself into something durable and dramatic. The Great Dark Spot discovered by Voyager 2 in 1989 seems at first to offer exactly the sort of anchor observers crave. Jupiter has its Great Red Spot. Neptune, it appears, has its own version, another long-lived vortex, another emblem of atmospheric power. The obvious explanation is that Neptune has permanent signature storms like the other giant planets, and that once such a system is found, the outer atmosphere becomes easier to track. The real problem is that Neptune refuses to stay that legible. When astronomers observe the planet again years later with more powerful telescopes, the Great Dark Spot is gone. Not weakened into insignificance. Gone. In its place, or elsewhere on the disk, other dark spots emerge, evolve and fade on timescales that make the planet feel less like a machine repeating a pattern and more like a system improvising under pressure. That is why Neptune's storms matter so much. They are not just spectacles of violence. They are proofs of instability in the very act of being studied. A storm that survives for centuries becomes a monument. A storm that appears and vanishes becomes a warning. It tells you the atmosphere is not only strong, but changeable in ways your models may not yet hold securely. The dark spots themselves are thought to be enormous anticyclonic vortices regions, where atmospheric flow organizes into rotating systems with lower cloud opacity, allowing deeper and darker layers to become visible. But even that description quickly begins to feel like a sketch, rather than an answer. What creates these vortices? What governs their lifetimes? Why do they drift in latitude? Why do some fade, while others seem to be born? Why are bright companion clouds often seen nearby, like brilliant fragments caught in the stress field of something much larger and darker? The answer seems clear until one tries to make it complete. Neptune's storms emerge from the interplay of internal heat, vertical mixing, atmospheric stratification, rapid rotation, and powerful zonal winds. But those ingredients do not combine in a way that gives observers the luxury of certainty. They give signs. They give tendencies. They give partial explanations. What they do not yet give is the satisfying feeling that the system has been closed. Neptune is not just stormy, it is evasively stormy. The bright clouds around these dark systems sharpen the sense of motion. These high methane ice clouds are sometimes called scooter clouds when they move rapidly through the atmosphere, racing along in nearby currents and hinting at the speed of the broader circulation. Their brightness is deceptive. They look decorative against the dark blue world. In reality, they are evidence of powerful vertical transport and shear material being lifted, cooled, condensed, and then carried through a hostile atmospheric architecture at extraordinary speed. They are not soft details. They are diagnostic flashes. Their presence means the atmosphere is not only spinning in giant hidden structures, but also punching upward through layers exposing the mechanics of weather in brief luminous signatures. Neptune's storms, therefore, have a double nature. The dark spots imply depth-hidden circulation and structural violence. The bright clouds imply height condensation and active uplift. Together, they reveal a world whose atmosphere is working in multiple dimensions at once. It is turning. It is rising. It is sinking. It is shearing itself into patterns that can endure for a while and then disappear before explanation catches up. That difficulty is intensified by scale and distance. On Earth, weather systems can be sampled by aircraft satellites, balloons, and dense networks of instruments, tracking pressure, temperature, humidity, and motion continuously. Neptune offers no such generosity. Humanity has one flyby and a long series of remote observations separated by immense distance and time. The planet is too far away for ordinary familiarity. The storms know it. They unfold in a domain where each clear observation feels precious and incomplete at the same time. This is why even the disappearance of a dark spot becomes scientifically dramatic. On a nearby world, a vanishing storm might be one data point among many. On Neptune, it becomes a statement about how little permanence can be assumed. In recent decades, telescopes, including Hubble and major ground-based observatories, have continued to detect dark spots on Neptune, some appearing at mid-latitudes, some drifting toward the equator, and some behaving in ways that are not fully predicted. In one especially intriguing pattern, a dark vortex observed in the late 2000s appears to reverse its usual equatorward drift, a behavior that complicates expectations about how such systems decay or migrate. Neptune keeps taking even provisional understanding and placing stress on it. The planet does not merely host weather. It tests atmospheric theory under conditions difficult to reproduce and impossible to visit routinely. And the longer one studies these storms, the wider the challenge grows. A dark spot is not just a localized event. It is a symptom of global circulation. A bright cloud is not just a visual accent. It is a marker of transport instability and thermodynamic consequence. A vanished storm is not just absence. It is evidence that the atmosphere reorganizes itself on timescales short enough to embarrass the word permanent and long enough to evade easy surveillance. Neptune's weather, therefore, does something rare in planetary science. It turns beauty into uncertainty. The more photogenic the storm system becomes, the more clearly it announces that the planet is not settled. It is a moving target in a place already difficult to observe. Storms do not happen in isolation from time. They belong to cycles, energy inputs, seasonal patterns, and long atmospheric histories. On Earth, a season can be felt within months. On Neptune, the meaning of a season stretches so far beyond an individual human rhythm that climate itself begins to take on the scale of inheritance. Neptune moves so slowly around the Sun that an entire human life is too small to witness even one ordinary year there from beginning to end. That fact sounds poetic at first, but its real consequence is methodological. It means Neptune is not merely hard to reach. It is hard to know in time. The planet takes about 165 Earth years to complete a single orbit, which stretches the meaning of season, climate, and atmospheric change into intervals far larger than the rhythms in which science usually learns. On Earth, seasons pass quickly enough to become memory. On Neptune, seasons become institutions. They outlast careers. They can outlast the people who begin observing them. The obvious explanation is simple distance. A planet that far from the Sun must travel along a vast orbital path, so of course its year is long. That is true, but it is the smallest part of the story. The real problem is what such a year does to interpretation. A planet whose sunlight changes only slowly across generations forces observers into an uncomfortable position. They are always early. They are always catching fragments. They are always trying to infer a long planetary sentence from a few visible words. Neptune is not just difficult because it is far away. It is difficult because its changes unfold on timescales that resist ownership by any single observer. Even the basic triumph of modern astronomy feels humbled here. Neptune is discovered in 1846, and only in 2011 does it complete its first full orbit around the Sun since that discovery. One full Neptunian year passes, and the human world that greets the completion is almost unrecognizable compared with the one that began the watch. Empires rise and fall. Technologies appear that the discoverers could not imagine. Entire scientific disciplines transform themselves. And Neptune, still moving through the same immense orbit, has only just returned to where the modern record started. This is what distance becomes when converted into time. Not emptiness, not silence, duration. A planetary scale so wide that the observer is made to feel temporary. Neptune's axial tilt, about 28 degrees, is not wildly different from Earth's, which means the planet does experience seasons rather than existing in some perfectly unchanging thermal arrangement. But the seasons there are enormous. Each one lasts for more than 40 Earth years. That means a seasonal shift on Neptune is not the passage from one school term to another, not the cycle of winter to spring, but something more like an epoch of atmospheric emphasis. A hemisphere leans toward the Sun for decades, then away from it for decades more. The sunlight is weak, yes, but the geometry still changes, and over time those changes can influence cloud patterns, haze, production, temperature, structure, and circulation in ways that are maddeningly slow to untangle. The answer seems clear until patience becomes part of the science. On a nearby world, researchers can build confidence through repetition. They can watch many cycles. They can compare one year with another. Neptune offers far less generosity. Even if one hemisphere brightens, even if cloud activity shifts, even if dark vortices appear preferentially in certain eras or latitudes, the record remains thin by the standards of a fully understood climate system. A few decades of good data on Neptune is not a completed archive. It is a glimpse inside one season. This distorts the observer's instincts. Human beings are trained by short cycles. We intuit weather because weather changes quickly. We build climate understanding because we can compare patterns across manageable spans of time. Neptune belongs to a slower register where even obvious patterns may be misleading because their full context has not yet come around again. It is possible to mistake a phase for a rule, a transition for a baseline, a temporary asymmetry for permanent structure. That is one reason Neptune keeps feeling scientifically unfinished. The planet is not withholding because it is passive. It is withholding because it is operating on timescales too long for convenience. Yet this slowness in orbit does not produce slowness everywhere else. That is another of Neptune's most revealing contradictions. The year is immense, but the winds can be ferocious. The seasonal rhythm is glacial by human standards, but storms can form, evolve, and disappear on much shorter timescales. Long climate and fast weather occupy the same world, forcing two kinds of time to coexist inside one atmosphere. A planet may drift around the Sun with grand patience, while local systems race through violent change above its hidden interior. This layered timing matters because it prevents any single explanatory frame from becoming sufficient. Neptune is not only a fast weather world, it is not only a slow season world, it is both at once, and the atmosphere visible at any given moment may reflect a mixture of temporary dynamics and longer solar geometry interacting with internal heat from below. What looks like a storm may carry the imprint of a season. What looks like seasonal change may be amplified or disrupted by a vortex. What looks stable may simply be moving too slowly to reveal its instability within a short record. That is why Neptune's long year is not a decorative fact to be dropped into a documentary and left behind. It alters the standard of proof. It reminds us that the planet's visible atmosphere is being watched through a temporal keyhole. Even the changing brightness of Neptune over recent decades and the evolving appearance of clouds and upper atmosphere features has to be interpreted with caution, because the world may still be teaching observers how slowly some of its large-scale patterns mature. The farther one goes into Neptune, the more observation begins to feel like inheritance. One generation starts the record, another extends it. A later one may finally learn what the earlier ones were actually seeing. This is the scientific cost of the outer solar system. Knowledge arrives in installments, and some installments are separated by decades. Neptune therefore expands the meaning of remoteness. It is distant not only in location, but in tempo. It lives on a clock that forces humility on anyone trying to reduce it too quickly. But time is only part of the concealment. Even if observers had centuries to watch every cloud and season, cleanly the deeper question would remain. Because the visible atmosphere is not the whole planet. It is only the upper expression of a world whose real strangeness increases with depth, where pressure rises so brutally that the familiar substances named in textbook descriptions are driven into forms no eye can see, and no simple analogy can hold. On Neptune, pressure does not merely compress matter, it rewrites it. That is the deeper descent the planet keeps forcing on anyone who tries to stop at clouds, winds, storms, and color. The atmosphere is dramatic, but it is not the real center of Neptune's strangeness. The real transformation begins below the visible weather, where the familiar substances used to describe the planet. In simple terms, water, ammonia, methane cease to behave in familiar ways. The obvious explanation is that Neptune is made of ices, and that beneath the atmosphere, those ices simply sit in colder, denser layers, like some enlarged frozen geology. The real problem is that the word itself misleads. In planetary science, ice refers less to texture than to chemistry, to volatile compounds that in the environment of the outer solar system condense more readily than hydrogen and helium. Inside Neptune, those materials are not resting in household forms. They are heated, compressed, ionized, mixed, and forced into regimes that no ordinary earthly intuition can visualize cleanly. Neptune is not a layered globe of neat categories. It is a pressure engine turning ordinary names into inadequate language. The descent begins with the upper atmosphere, where hydrogen, helium, and methane dominate what can be seen. But there is no meaningful solid surface waiting beneath the clouds, no clear line where one could say the atmosphere ends and the true planet begins. Pressure rises continuously. Temperature rises with it. Gas gives way to fluid-like states. The distinction between air and ocean, between cloud world and interior world, starts to dissolve. Deeper down, planetary models suggest a vast mantle region, rich in water, ammonia, and methane, though mantle here should not be mistaken for Earth's rock mantle. This is not a world of tectonic plates, crustal rigidity, and rocky convection in any terrestrial sense. Neptune's middle depths are more alien than that. A massive envelope of hot, dense, electrically active fluid, under crushing pressure perhaps best imagined, not as a place of layers stacked tidally, but as a domain where chemistry, heat, and motion are trapped together, in forms almost no direct human experience prepares the mind to hold. This is where the planet stops resembling a bigger Earth or a smaller Jupiter, and becomes something more difficult, a world built from familiar ingredients, transformed beyond recognition. Water, for example, is one of the most common words in any description of Neptune's interior. Yet the water there is not the water of oceans, rain, or ice sheets. Under the temperatures and pressures expected deep within the planet, water may enter ionic or superionic states, phases in which molecules break apart, atoms reorganize, and electrical behavior becomes part of the planetary architecture. Oxygen can form lattice-like structures, while hydrogen ions move through them in a way that sounds less like ordinary matter and more like matter under interrogation. These are not decorative extremes. They may affect how heat is transported, how the interior convects, and how the planet generates its magnetic field. The answer seems clear until matter itself changes category. The same is true of methane and carbon-bearing compounds. Deep inside Neptune, conditions may become so extreme that carbon is forced out of simpler molecular arrangements and into denser forms. One of the most striking hypotheses is that carbon there may crystallize into diamond-like material and sink deeper through the planet. The popular phrase is diamond rain, and it is memorable for good reason. But what matters scientifically is not the romance of falling gemstones. It is the implication that Neptune's interior may be chemically separating itself under pressure, redistributing mass and perhaps releasing gravitational energy as heavier material moves downward. The image is dramatic, but the mechanism is the real point. Pressure does not only squeeze, it sorts, it reorganizes. It turns composition into motion, and motion in a giant planet is never a local curiosity. It scales upward into global consequence. The deeper one goes, the harder it becomes to think in stable pictures. Neptune may possess a rocky core at the center, perhaps a few Earth masses in size, surrounded by these immense volatile-rich layers. Yet even this interior sketch remains an inference built from mass radius. Gravity measurements, thermal behavior, magnetic clues, and theoretical modeling. No probe has descended through Neptune's atmosphere into its mantle. No instrument has sampled these depths directly. The planet's hidden world is reconstructed from evidence at a distance, and that gives the science both its discipline and its tension. Models must be physically plausible. They must match what the planet reveals from the outside. But plausibility is not the same as finality. Neptune may still be stranger than the best current diagrams suggest. That matters because pressure is not a side detail of giant planets. It is one of the forces that decides what kind of world the planet can become. On Earth, pressure shapes geology. On Neptune, it shapes the meaning of matter. It determines which layers mix and which resist mixing. It affects whether heat can rise efficiently or gets trapped below. It changes conductivity, chemistry, and density. It may help explain why Neptune's interior seems more willing than Uranus's to leak energy outward. It almost certainly helps explain why the planet's hidden engine does not translate into a simple arrangement above. Neptune's visible atmosphere looks like the outermost skin of a coherent globe. But beneath that skin, the world is likely a dynamic, deep fluid system under such intense compression that ordinary categories blur together. In that sense, Neptune is not only far away in space and slow in season, it is far away in state. It occupies physical regimes only partially reproduced in laboratories and never directly seen by human eyes. That distance in state may be the most important distance of all, because it means Neptune is not just remote. It is materially alien. And once that becomes clear, another visible mystery stops looking accidental. Because if the interior really is this deep, this electrically active, this compositionally unusual, and this dynamically strange, then the planet's magnetic field should not behave like a neat centered dipole. It should emerge distorted, displaced, and unsettlingly off balance as if the hidden structure is refusing symmetry, even in the invisible geometry that surrounds the whole world. Neptune's magnetic field does not behave like the invisible halo of a well-ordered planet. It behaves like a warning from the interior. For a long time, the easy assumption about planetary magnetism is symmetry. A planet spins. Deep conductive material moves. A magnetic field forms in a broad dipole, roughly aligned with the rotation axis, centered near the heart of the world, extending outward, in a shape that, while dynamic and imperfect, still feels structurally intelligible. Earth broadly fits that intuition. Even Jupiter, for all its scale and violence, still presents a magnetic system that can be described in ways that feel continuous with the standard story of a planetary dynamo. Neptune does not. When Voyager 2 flies past the planet in 1989 and measures its field, it finds something far stranger. The magnetic axis is steeply tilted relative to the planet's spin axis, and the field is significantly offset from the geometric center of the world. This is not a small technical wrinkle. It is a structural insult to the neat model. The obvious explanation is that Neptune simply has a magnetic field with some eccentric geometry, a statistical oddity to be catalogued and moved past. The real problem is that magnetic fields are not decorative. They are generated by motion inside matter. If the field is this peculiar, the interior engine creating it must also be peculiar. That is why Neptune's magnetism matters so much. It is not just one more planetary property. It is one of the clearest signs that the hidden world below the clouds is not arranged in the centered, orderly way casual intuition prefers. Neptune's magnetic dipole is tilted by roughly 47 degrees relative to the rotation axis, and the field appears displaced well away from the planet's center. That means the magnetosphere Neptune projects into space is not the clean, evenly balanced envelope one might imagine around a smooth blue giant. It is skewed asymmetric and constantly changing its relation to the solar wind as the planet rotates. Because Neptune spins in about 16 hours, a lopsided magnetic geometry means the surrounding space environment is being swept through a strange cycle over and over again, with the field presenting different faces and strengths to the oncoming stream of charged particles from the Sun. This creates a magnetosphere that is not merely large, but dynamically awkward. The planet's invisible environment turns with a wobbling logic, as if the hidden engine generating it is mounted wrong inside the body. But wrong is only a human word for a pattern that refuses our preferred symmetry. In Neptune's case, the deeper lesson is harsher. The field is telling us that the dynamo region inside the planet is probably not deep at the exact center in the way once assumed for simpler models. Instead, the magnetic field may be generated in a comparatively shallow shell of electrically conducting fluid, perhaps in those hot, compressed water-ammonia-rich layers where pressure has forced matter into unusual ionic states. That possibility changes the picture completely. If the conductive material responsible for the field exists in a shell rather than in a large central metallic region, then the resulting magnetic geometry can become multipolar off-center and dramatically tilted. The field stops looking like a single bar magnet hidden inside a sphere and starts looking like the outcome of convection in an uneven, shifting outer interior engine. The answer seems clear until the invisible geometry begins to imply a new interior map. Neptune's magnetism therefore acts like a translator between inaccessible depth and observable consequence. No one has seen the dynamo layer directly. No probe has entered the planet and returned a clean diagram of moving conductive fluids. Yet the field extends into space where instruments can measure it, and from that measurement comes a profound inversion. The atmosphere may be the most visually dramatic part of Neptune, but the magnetic field is often the more revealing one. Clouds can deceive because they are only the upper skin. Magnetism reaches deeper. It exposes the fact that the interior is not simply pressurized, but organized in unfamiliar ways. What looks like a rounded blue globe from afar may, in its active depths, be a far less centered thing. That has consequences beyond theory. A strange magnetic field shapes how charged particles move around the planet. It influences radiation belts, auroral behavior, and the way Neptune interacts with the solar wind and with material in its surrounding environment. On Earth, auroras are tied to a magnetic geometry that channels particles toward the poles in broadly expected ways. On Neptune, the severe tilt and offset mean that auroral processes likely occur in a more complex spatial arrangement, less obedient to the tidy polar storytelling familiar from terrestrial experience. Even here, Neptune refuses the easy visual. The field does not merely protect or surround. It distorts the relationship between planet and space. It means that Neptune is not only meteorologically strange below the sunlight, but electromagnetically strange beyond the atmosphere. The world affects its environment through an invisible asymmetry that rotates relentlessly through the dark. This makes the field more than an internal clue. It becomes a system-level expression of hidden disorder. And that expression is especially important because Neptune's magnetic weirdness is not unique in isolation. Uranus also has a bizarrely tilted and offset magnetic field. The apparent sibling planets, already linked by class and bulk composition, now reveal a second family resemblance. Both are giant worlds, whose deep interiors generate magnetism in a way that seems fundamentally different from Earth, Jupiter, or Saturn. That suggests the ice giants are not merely smaller alternatives to gas giants. They may represent a distinct magnetic regime in planetary physics, one where conductivity, convection, geometry, and composition produce fundamentally off-center worlds. In that sense, Neptune's field is not just about Neptune. It is about what kinds of planets the universe can build when matter is compressed into volatile, rich, electrically active layers and allowed to circulate under enormous pressure. The smooth visual face disappears again. Underneath it lies not a centered globe, but a hidden engine working from displaced layers, producing an invisible architecture as strange as the weather above it. And there is a final consequence to that realization. A world whose magnetic field is this misaligned, whose storms are this violent, and whose interior is this difficult to simplify, begins to look less like an isolated curiosity and more like the survivor of a complicated past. Because planets do not become this strange in a vacuum. Their present structure often carries the scars of formation, migration, collision, and capture. And around Neptune, one of the clearest surviving signs of that violent history is not in the planet itself, but in the great moon that should never have belonged to it so neatly in the first place. Triton is not just Neptune's largest moon. It is evidence that the outer solar system did not settle into order gently. At first glance, moons can look like supporting characters, secondary bodies circling the larger world that truly matters. Neptune itself seems large enough, strange enough, and atmospheric enough to command the whole story without help. The obvious explanation is that Triton is simply one more major moon in a giant planet system, another frozen companion formed in place from the same circumplanetary material that helped assemble the planet's smaller attendants. The real problem is that Triton does not move like a moon that belongs naturally to Neptune in that simple way. It orbits in a retrograde direction, meaning it travels around Neptune opposite to the planet's rotation. That single fact fractures the easy story. Large moons that form quietly from the disk of material around a young giant planet are expected to orbit in the same general direction as the planet spins. Triton does not. It moves against the order one would normally expect, and because of that, it carries the force of a historical clue. Triton is almost certainly a captured world, a body that forms elsewhere and is later seized by Neptune's gravity. That changes everything. A captured moon is not a decorative addition. It is the surviving result of a dynamical disturbance powerful enough to rewrite an entire planetary system. Triton therefore matters not only because of what it is, but because of what its existence implies. Neptune must once have done. Capture on this scale is not a tidy event. Triton is larger than Pluto, round under its own gravity, and complex enough to look less like a minor moon than like a displaced dwarf planet. A body that's substantial does not simply drift into place and begin orbiting harmlessly. To become bound to Neptune, it likely has to lose energy through a dramatic interaction, perhaps involving a binary object encounter in which one member escapes and Triton remains trapped, or some similarly disruptive early system process. However exactly it happens, the consequence is clear. Neptune's original satellite system does not survive such an arrival unchanged. A massive captured moon descending into the system on a hostile orbit would gravitationally destabilize pre-existing moons, scatter some inward or outward, perhaps destroy others entirely, and leave the planet with a reorganized entourage built partly from loss. The story on the surface is one moon. The story underneath is planetary violence. Triton is the survivor of a celestial coup. That matters because Neptune already appears from its interior and atmosphere like a world whose present state is shaped by deeper forces hidden from easy view. Triton extends that principle outward into orbital history. The moon's existence says Neptune is not only meteorologically strange and magnetically strange, it is historically scarred. The system we see today is not just the natural growth of a quiet outer giant. It is the residue of captured disruption and reconstruction. Even Neptune's current smaller inner moons may tell that story indirectly. Their close-in prograde orbits and irregular characteristics can be understood as the remnants or reassembled debris of a system altered after Triton's arrival. In other words, Neptune may once have had a more ordinary family of moons, and Triton may have broken it apart. That is the deeper cost hidden behind the present arrangement. The moon itself then becomes even more unsettling, because Triton is not merely a captured relic frozen into passivity. Voyager 2 finds a world that is geologically surprising, with a thin nitrogen atmosphere, an exceptionally cold surface, and evidence of active processes, including nitrogen geyser-like plumes rising above the terrain. This is not the behavior of a perfectly dead captured object. Triton preserves energy or activity of some kind, perhaps through seasonal heating of surface volatiles, perhaps through deeper internal processes, perhaps through the long after-effects of tidal evolution earlier in its history. The obvious explanation is that distant icy bodies should be inert. Triton answers with motion. The moon's strange cantaloupe-like terrain, smooth plains, sparse crater counts in some regions, and volatile frosts suggest resurfacing and change, which means Neptune's greatest captured prize is not just a fossil of ancient violence, but a world with its own continuing story. And because Triton is so unusual, it also widens the significance of Neptune beyond the planet itself. This is not merely a giant world with weather. It is the center of a system that contains one of the most compelling captured objects in the solar system, a body that links Neptune to the Kuiper belt and to the broader history of migrating, interacting outer worlds. Triton feels like a message from beyond Neptune because, in a sense, it is. It may be the most visible proof that the boundary between planets and small body populations in the outer solar system is not clean. Worlds can be exchanged, systems can be invaded, orbits can be turned backward. The outer solar system is not a static row of isolated spheres. It is a history of encounters. There is also a future cost hidden inside Triton's orbit. Because the Moon travels, retrograde tidal interactions are not stabilizing it forever at a comfortable distance. Instead, over immense timescales, Triton is expected to spiral gradually inward toward Neptune. Far in the future, it may cross the Roche limit and be torn apart by tidal forces, creating a massive ring system around the planet before its material perhaps rains downward or reforms in smaller bodies. Even Neptune's present calm arrangement therefore contains a delayed catastrophe. The captured moon that once destabilized the system may one day be destroyed by the planet that seized it. This is what Triton really adds to Neptune's meaning. It takes a world already defined by hidden heat, violent atmosphere, deep pressure, and off-center magnetism, and shows that its orbiting history is just as unstable beneath the surface story. Neptune is not merely a blue giant at the edge. It is a system assembled through conflict and still carrying the consequences of that conflict in motion around it. And once Triton enters the picture, a larger humiliation follows. Humanity speaks about Neptune as though it has been substantially studied, yet almost everything vivid in this whole account of planet and moon still depends on a single brief encounter, one flyby, passing through the darkness and leaving behind a record much richer than what came before, but still painfully smaller than what remains unknown. Almost everything humanity vividly knows about Neptune comes from a single close encounter that lasted only a few days. That is not a rhetorical flourish. It is the central embarrassment of the entire subject. A planet more than 17 times the mass of Earth wrapped in violent winds, strange magnetism, deep pressure, physics, and a captured moon that rewrites system history has been visited closely only once by Voyager 2 in August 1989. The obvious explanation is that a flyby combined with telescopes is enough to establish the broad character of a distant giant world. And in one sense, that is true. Voyager 2 transforms Neptune from a faint blue disk into a living planetary system. It reveals the great dark spot, bright high clouds, complex rings, small moons, the active and astonishing Triton, the tilted magnetic field, and the broad atmospheric dynamism that changes the planet's meaning permanently. But the deeper problem is scale. One flyby can reveal a world. It cannot finish one. It gives a burst of proximity, a single crossing through space and time, one geometry, one season, one phase of the atmosphere, one set of instrumental opportunities, and then it leaves. Neptune remains behind, still rotating, still storming, still radiating internal heat into the dark, still evolving on timescales far longer than the encounter that defined it for a generation. That is why Neptune is not merely understudied. It is structurally underexperienced. We have seen it up close once, and from that one pass, we have been forced to build a long narrative of a planet far larger and more complicated than the data window that first illuminated it. This creates a dangerous illusion of completeness. Voyager is so legendary and its images so iconic that the mind begins to feel as though Neptune has been meaningfully entered into human knowledge. the achievement is real. The cost is larger. Because when a single mission becomes the foundation of planetary intimacy, everything learned afterward is burdened by comparison with that one moment. The planet is known through a narrow aperture, and the more important the planet becomes scientifically, the more painfully narrow that aperture appears. Even modern telescopes, powerful as they are, do not erase this limitation. The Hubble Space Telescope, large ground-based observatories with adaptive optics, infrared facilities, and improved image processing have all extended Neptune's record dramatically. They have tracked clouds, dark spots, brightness changes, seasonal evolution, atmospheric temperatures, and aspects of chemistry. These observations matter enormously. They allow Neptune to be watched rather than merely remembered. But remote sensing from Earth's neighborhood, no matter how advanced, is still not the same as dwelling near the planet. It cannot provide the continuous in situ measurements of atmospheric structure, composition, wind fields, magnetic dynamics, interior gravity, harmonics, ring particle environments, and moon-by-moon geological context that an orbiter entry probe or long-duration system mission could deliver. The answer seems clear until instrumentation becomes part of the story. Humanity does not merely lack facts about Neptune, it lacks the right kind of sustained presence, and that absence shapes the science everywhere. Storms are observed but not sampled from within. Heat flow is inferred, not mapped in full detail. Magnetism is measured from one flyby geometry and constrained by models rather than revisited over many years in orbit. Triton is seen as an active, compelling world, but not returned to with the tools modern planetary geology would demand. The rings are known to be faint and structured, but not followed closely enough to understand all their dynamics. Even the atmospheric composition above and below the visible clouds remains less secure than the public image of Neptune's elegance might suggest. A planet this influential should feel closer to certainty than this. Instead, it keeps reminding us that recognition is not mastery. The reason this matters is not only that Neptune itself is interesting, though it clearly is. The deeper issue is that Neptune may be one of the most important comparative worlds in the solar system for understanding giant planets as a whole. Jupiter and Saturn are magnificent, but they are not the only way giant planets exist. Neptune and Uranus define the ice giant class, and if those worlds remain poorly constrained, then planetary science carries a blind spot at the level of categories. We know the inner rocky planets relatively well. We know the large gas giants comparatively well. But the outer volatile rich giants, the intermediate planetary architecture between Earth-like and Jupiter-like extremes, remain incompletely grasped. That is not a minor omission. It is a gap in the grammar of planet formation. Neptune therefore becomes a paradox of modern exploration. It is too important to ignore, too far to visit casually, too data poor to settle comfortably, and too scientifically rich to leave alone forever. Mission concepts have appeared across the years. Ideas for Neptune orbiters, atmospheric probes, Triton lander system tours, but distance, cost, time, and institutional priority have repeatedly deferred the return. This is what outer solar system science does to ambition. Every serious mission becomes a generational wager. Travel takes many years. Budgets swell. Payload decisions harden early because repair is impossible. By the time a spacecraft arrives, entire careers may have passed. Neptune stretches not only observation, but planning itself. It forces human institutions to think in longer arcs than they prefer. And that may be one reason it remains so intellectually haunting. The planet exposes a limit in modern civilization's relationship with knowledge. We are capable of seeing that Neptune matters. We are not always capable of sustaining the patience required to know it properly. So the result is a world suspended between revelation and neglect, rich enough to transform planetary theory, remote enough to remain half abstract, famous enough to be recognized instantly, unfinished enough that almost every major feature opens into a longer question. Neptune is not a solved planet waiting for better photography. It is a partially entered domain whose most vivid truths still rest on a single passing witness. And that would already be enough to make it scientifically frustrating. But the deeper consequence is larger still. Because Neptune is not only a remote member of our own solar system. Worlds roughly in its size range appear again and again around other stars, which means this distant planet may be one of the most valuable local keys humanity possesses for understanding one of the most common planetary forms in the galaxy. Neptune may look like the distant exception in our own solar system, but beyond the Sun, it begins to look disturbingly normal. That is one of the deepest reversals in the entire story. For generations, the public imagination is shaped by the planets it can name in order: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. In that lineup, Neptune feels like the terminal case, the last blue giant at the outer margin. Remote enough to seem almost ceremonial, more frontier marker than planetary template. The obvious explanation is that Neptune is interesting because it is far away and strange. The real problem is that modern exoplanet astronomy has quietly made Neptune important for the opposite reason. It may not be strange in the rare sense. It may be strange in the revealing sense. Again and again, surveys of planets around other stars uncover worlds whose sizes and masses fall roughly into the range between Earth-like rocky planets and Jupiter-like gas giants. Sub-Neptunes and Neptune-like planets appear with remarkable frequency in the galactic record. Some are hotter, closer to their stars, and very unlike our own cold outer giant in temperature or irradiation. Some are denser, some are puffier, some may have thick atmospheres over deep volatile layers, but the essential pattern is what matters. The universe seems very willing to build planets in this middle regime. Our own solar system, by contrast, offers only Uranus and Neptune as local examples. That means Neptune is not merely a curiosity at the edge of our system. It is one of the nearest laboratories for one of the most common broad categories of planet nature seems to produce. The story on the surface is local. The story underneath is cosmic. This changes the stakes of ignorance immediately. If Neptune-like worlds are common, then failing to understand Neptune is not just failing to understand one distant planet. It is failing to understand an entire mode of planet-making that the galaxy may favor. And that failure is more consequential than it first sounds, because exoplanets are often known only through indirect measurements, a radius from a transit, a mass from stellar wobble, perhaps a hint of atmospheric composition from transmission spectra if the conditions are favorable. Those signals are precious, but thin. To interpret them, scientists need grounded physical understanding of how planets of a given size composition and thermal history actually behave. Neptune is one of the few places where such understanding can in principle be anchored by a real nearby world. But anchoring requires depth, and Neptune is precisely where depth remains incomplete. The answer seems clear until comparison begins. What does it mean, for example, when an exoplanet is labeled Neptune-sized size? Alone does not tell you whether the world is dominated by a hydrogen-helium envelope, whether it contains a deep volatile mantle, Whether its atmosphere is stripped or inflated, whether its internal heat is escaping efficiently, whether its magnetic field is orderly or bizarre, whether its chemistry is stable or violently mixed, or whether its visible appearance conceals far stranger layering below. Neptune itself should have cured us of that simplification by now. A planet can occupy this size range and still be hiding storms, thermal anomalies, conductive fluid shells, deep phase transitions, and a history of capture and disruption in its surrounding system. Once that lesson is learned locally, exoplanet catalogues stop looking like lists of points and start looking like fields of unresolved worlds. Neptune, therefore, has a second importance beyond its own system. It teaches caution. It warns against overconfidence when categories become too tidy. A world measured at 4 Earth radii is not automatically understood because the number is known. A bulk density suggests possibilities, but it does not narrate the interior. An atmospheric spectrum reveals pieces, not the whole machine. Neptune shows how much can remain hidden even when a planet is close enough to image as a disk track through seasons and visit with a spacecraft. What then must still be hidden in planets seen only as transits and spectral traces? That is why Neptune matters as a bridge world. It stands between the intimate and the inferential, between local observation and galactic statistics. It is close enough to matter physically and far enough to remain difficult, and those two facts make it unusually valuable. Neptune also challenges a deeper assumption inherited from the solar system itself. For a long time, planetary understanding is built from a limited menu, small rocky worlds, inside giant gaseous worlds outside. But exoplanet discoveries reveal that this menu is incomplete. There are many planets with no exact solar system twin, especially in the size regime between Earth and Neptune. Some of the most common worlds known in the galaxy appear to have no perfect local counterpart at all. That makes Neptune even more important, not less. It becomes one of the nearest approximations to a broader class of planetary possibilities, a world that may help decode bodies we can never visit directly. If Neptune remains underexplored, then one of the best keys we possess for interpreting these common extrasolar worlds is still only half-turned in the lock. That is an uncomfortable scientific position. We are cataloguing the galaxy faster than we are grounding our categories. We are finding planetary abundance faster than we are explaining planetary nature. Neptune sits inside that tension like an accusation. It says, "You have seen many worlds like my general size, but you do not yet fully understand what one such world is doing next door." And that accusation only grows stronger the more exoplanet science advances, because each new Neptune-like detection expands the population while widening the interpretive burden. The blue giant at the edge of our own system therefore stops being peripheral. It becomes central in a subtler way, not the center of public attention, not the center of the solar system, but the center of a missing comparative framework, a world whose atmosphere, heat flow, interior structure, and magnetism may all be teaching lessons the exoplanet era cannot afford to treat as optional. Neptune begins as the last named giant. It becomes one of the first serious tests of whether human planetary science can move from classification to understanding across worlds. And that is where the strain tightens again, because once Neptune is asked to carry this larger comparative burden, the easy explanations begin failing even more visibly. Simple models of giant planets, simple labels about ice and gas, simple assumptions about heat, wind, and structure, all of them start to crack under the weight of what Neptune is and what Neptune-like worlds may be forcing us to learn. Neptune keeps breaking the explanations that should have made it manageable by now. That is the larger pattern hidden beneath every individual mystery. Taken one by one, each problem can seem containable. The winds are extreme, but perhaps internal heat can account for them. The color is unusually deep, but perhaps methane and haze structure explain that. The storms form and vanish, but perhaps atmospheric dynamics under rapid rotation naturally produce such behavior. The magnetic field is severely tilted and offset, but perhaps a shallow conductive shell can generate that geometry. The interior is strange, but perhaps compressed volatile-rich layers under high pressure are simply what ice giants do. The obvious explanation is therefore cumulative. Each anomaly has a technical explanation, and once enough specialist papers exist, Neptune will settle into place as one more complicated but essentially solved planet. The real problem is that the planet's complications do not remain separate long enough to be domesticated that way. They interfere with one another. They amplify one another. They expose the weakness of any model that tries to hold one layer steady while treating another in isolation. Neptune is not difficult because it contains one puzzle. It is difficult because its puzzles form a system. Internal heat is not just a thermal issue. It affects convection, which affects atmospheric circulation, which affects cloud formation, which influences visible appearance, which complicates the interpretation of remote data. Deep composition is not just an interior issue. It affects density structure, electrical conductivity, magnetic generation, and the pathways through which heat can escape. Rotation is not just a timing fact. It helps organize wind storms and magnetic asymmetry into large-scale patterns that change how the entire world behaves. Even Triton is not just a moon problem. It alters the historical frame, reminding us that formation and later dynamical violence may have shaped Neptune's present condition in ways not cleanly separable from what the planet is now. The answer seems clear until everything begins connecting to everything else. That is where easy planetary storytelling fails. Planetary science often advances by simplifying a world enough to isolate a mechanism. This is necessary. No model can begin by including every variable. But with Neptune, the cost of simplification appears unusually high. A model of wind that treats the interior too crudely may miss the energy pathways that matter. A model of interior structure that treats mixing too cleanly may miss the magnetic consequences. A model of atmospheric appearance that assumes optical properties are passive may misread signs of vertical dynamics. Neptune keeps punishing the urge to separate what the world itself has braided together. It is not that scientists know nothing. Far from it. The body of knowledge is real, disciplined, and cumulative. But the more those pieces are assembled, the more they begin to reveal how much of Neptune depends on linked processes, rather than isolated features. This makes Neptune harder in a way that is philosophically important, not just technically frustrating. It is one thing to be ignorant because data are missing. It is another to realize that even with more data, the world may still resist neat explanation because the categories used to understand it were too cleanly divided to begin with. Neptune does not just wait for better measurements. It forces a more entangled style of planetary thinking. Consider the thermal problem again. Neptune radiates much more energy than it receives from the Sun. That fact is robust. But why does it do so more effectively than Uranus? The moment one tries to answer the problem expands. Perhaps the interior is more convective. But what sets the efficiency of convection composition gradients? Phase behavior, layer stability, heat transport properties, historical evolution. maybe even formation conditions or later impacts. The same planet that first appears as a blue weather disk is suddenly asking questions about billions of years of internal development. Or consider the magnetic field. A shallow shell dynamo may broadly fit the observed geometry, but the moment that idea is taken seriously, new demands appear. What is the exact conductivity structure of the relevant layers? How does convection work there? How stable are those layers over time? What role do supersonic or ionic phases play? How much asymmetry is locked in by composition versus generated dynamically? Again and again, Neptune refuses local answers. Every path downward opens sideways. That is why the easy explanations fail. Not because they are foolish, but because each one is too small for the scale of the thing it tries to contain. Even public language starts to fray under this pressure. Ice giant is useful, yet hides how unlike familiar ice the deep planet actually is. Blue is accurate, yet conceals how much atmospheric structure and motion are folded into that appearance. Storms is correct, yet sounds too Earth-like for dark vortices moving through an atmosphere powered partly from below. Internal heat is factual, yet dangerously vague if it suggests a simple buried furnace instead of a layered planetary engine. Neptune teaches repeatedly that the labels used to begin understanding can become obstacles if mistaken for conclusions. This is not a problem unique to Neptune, but Neptune dramatizes it with unusual force because the world is both visually clean and physically unruly. It invites simplification aesthetically and then defeats it scientifically. And that defeat matters beyond one planet. In the exoplanet era, where countless worlds are interpreted through sparse data and broad categories, Neptune becomes a warning against category comfort. If this nearby ice giant cannot be reduced without remainder, even after telescopes, a flyby decades of theory and comparative planetology, then every Neptune-like world beyond the solar system may be carrying hidden differences, large enough to alter the interpretation entirely. The cost of a bad simplification is no longer local. It radiates outward into the way humanity reads whole populations of planets. Neptune then becomes more than a scientific puzzle. It becomes a pressure test for our methods. Can planetary science move beyond naming classes and sketching average behaviors? Can it learn to think in layered systems where atmosphere, chemistry, magnetism, history, and deep state matter are all allowed to shape one another? Neptune does not answer politely. It answers by staying unresolved. And that unresolved state points toward the next and perhaps hardest layer of all. Because once the easy explanations fail repeatedly, the question is no longer just what Neptune is doing. The question becomes what the limits of our current planetary imagination are, and what it costs to face a world that keeps revealing those limits without yet surrendering to them. Neptune does not merely reveal a distant planet. It reveals the boundary of the mindset that first approached it. That is the larger meaning waiting beneath the atmospheric facts and interior models. And it is why this world grows more consequential the longer one thinks about it. At the start, Neptune seems like an object problem. One planet, one set of measurements, one distant giant to describe accurately enough that it can be placed inside the order of the solar system. The obvious explanation is that once enough observations accumulate, the world will settle into knowledge just as other planets have, and the primary difficulty will be technical rather than conceptual. Better instruments, better spectra, better models, perhaps a future orbiter and probe, and the remaining uncertainties will slowly shrink. That is partly true. Better data will matter immensely. But the deeper problem is that Neptune has already shown the limits of a certain style of seeing, one that mistakes naming for understanding, category for mechanism, appearance for structure, and distance for absence. The planet keeps exposing those habits because almost every intuitive simplification collapses on contact. Cold does not mean inactive. Blue does not mean simple. Remote does not mean empty. Giant does not mean Jupiter-like. Even known does not mean deeply entered. Neptune stands at the edge of the solar system like a rebuttal to every explanation that becomes comfortable too early, and that makes it more than a scientific target. It becomes a philosophical pressure point inside planetary science itself. The story on the surface is one of outer darkness. The story underneath is one of human-scale failure. Neptune asks questions at distances too large for immediate intuition, in materials too compressed for common analogy, on timescales too long for direct familiarity, and through a data record too sparse for complacency. In other words, the planet forces a confrontation with the fact that not all realities become legible on human terms, simply because they are mathematically describable. A model can fit observed behavior and still leave the world feeling physically ungrasped. A category can be correct and still conceal the decisive layer. A map can improve while the territory continues to resist closure. Neptune does not invalidate science. Quite the opposite. It vindicates disciplined science by showing why discipline is necessary. It shows why humility is not rhetorical modesty, but operational necessity when dealing with systems that exceed the scale of ordinary experience. There is also a civilizational dimension to this. Human culture often treats discovery as a sequence of thresholds. Crossed permanently, a planet is found, mapped, classified, and thereby incorporated into a usable world picture. Neptune resists that neat triumphalism. Its discovery is brilliant, its flyby historic, its subsequent observation rich, and yet the planet remains only partially domesticated by knowledge. That is not a failure of intelligence. It is a reminder that some domains remain structurally resistant to quick incorporation. They demand long memory, institutional patience, generational continuity, and a tolerance for unfinished understanding. Neptune therefore becomes a test not just of theory, but of endurance. Can a civilization remain intellectually attached to a question whose answer will likely unfold across decades, missions, and inherited records? Can it keep caring about a world that does not offer easy completion? These are not ornamental questions. They decide what kinds of knowledge humanity is actually capable of building. The farther the object, the more temptation there is to be satisfied with a poetic summary in place of a physical one. Neptune is blue. Neptune is windy. Neptune is mysterious. All true, all insufficient. The planet keeps demanding a harder form of attention, one willing to follow consequence, downward into hidden layers and outward into wider implications. It asks for a scale of thought that links atmospheric motion to interior chemistry, deep state matter to magnetic geometry, moon capture to system history, local ignorance to exoplanet interpretation. That is why Neptune feels larger than its size alone. It does not only occupy space, it occupies explanatory burden. Once this is recognized, the unresolved pressure surrounding the planet becomes part of its meaning. Neptune is not compelling despite being unfinished. It is compelling because its unfinished state reveals something essential about how reality exceeds the first frameworks used to organize it. This is the cost that sits behind all the beauty. The blue disk has become iconic, but what it really represents is the persistence of hidden structure behind visual coherence. The world looks composed, yet contains violence. It looks distant, yet bears directly on the interpretation of countless exoplanets. It looks named, yet remains partly unsurrendered. It looks like a final member of a completed family, yet still destabilizes the family categories themselves. Neptune is therefore one of those rare scientific objects that becomes more meaningful as certainty gives way to layered incompletion. Not because uncertainty is romantic, but because uncertainty handled honestly reveals the size of the real thing. A fully solved Neptune might still be magnificent. But the Neptune we actually have is something sharper, a world that continuously widens the frame of its own importance. It begins as the far giant. It becomes the weather paradox, then the thermal anomaly, then the pressure laboratory, then the magnetic warning, then the captured system survivor, then the exoplanet key, then finally the mirror held up to our own methods of understanding. And that progression matters because the final revelation is not really about Neptune alone. It is about what happens whenever human beings approach a beautiful distant system and discover that every neat answer was merely the outer atmosphere of a much deeper truth. Neptune teaches that lesson with unusual force because it never stops at one scale. It is intimate in detail and enormous in implication at the same time. A dark vortex can lead to a question about deep heat transport. A blue color can lead to a question about atmospheric structure. A tilted field can lead to a question about the state of matter under extreme pressure. A captured moon can lead to a question about the violence of planetary histories. The world keeps enlarging itself through connection, and once that enlargement is seen clearly, one final turn becomes unavoidable. Neptune no longer appears as the last quiet giant waiting politely at the margin of the solar system. It appears as one of the places where the margin itself collapses, where distance stops meaning emptiness and begins meaning hidden energy, unfinished knowledge, and a planetary reality far more alive than the opening image ever promised. Neptune looks like an ending, but it is really a beginning disguised as distance. That is the final reversal. At the start of this story, the planet seems almost too far away to matter, except symbolically, a blue world dimmed by weak sunlight, and stranded at the margin of the solar system, the kind of place the mind reduces quickly because reduction feels efficient. It is the last giant, the outer dark, the cold frontier. The obvious explanation is that Neptune marks the point where planetary drama begins to thin out, where sunlight fades and worlds become less urgent because they are less available to ordinary human imagination. The real truth is the opposite. Neptune is one of the places where the solar system stops being easily narratable and starts becoming fully planetary. It is where the outer darkness refuses passivity. It is where cold and violence coexist. It is where beauty stops being a summary and becomes a mask. It is where a planet first mistaken for a remote object reveals itself, layer after layer, as a living argument about how worlds store energy, how matter changes under pressure, how atmospheres betray interiors, how capture rewrites systems, and how ignorance can survive even after discovery. Neptune does not close the story of the planets. It reopens it from the far side. By now, the pattern is unmistakable. The blue disk suggests calm, yet the atmosphere runs with ferocious speed. Weak sunlight suggests thermal poverty, yet the planet radiates more energy than it receives. The category ice giant suggests manageable composition, yet the interior likely contains states of matter so altered by pressure that common language begins to fail. The smooth globe suggests symmetry, yet the magnetic field is tilted and displaced, announcing a hidden engine that does not sit neatly at the center. The Moon system suggests ordinary giant planet order, yet Triton reveals capture, disruption, and a history of violence still written into orbit. The thin observational record suggests distance should make the planet peripheral, yet exoplanet science turns Neptune into one of the most important comparative worlds we have. Again and again, the accepted explanation arrives first, and again and again. Neptune shows that the accepted explanation is only the outer shell of a deeper one. That repeated structure is the real subject of the planet. Neptune is not merely a collection of mysteries. It is a machine for exposing shallow understanding. Some planets become familiar through repeated observation. Neptune becomes powerful through resistance. It stays alive intellectually because it keeps widening the cost of stopping too soon. This is what transforms Neptune from a distant fact into a planetary lesson. The lesson is not simply that the solar system contains strange worlds. We already know that. The lesson is that strangeness is often organized, layered, and initially invisible. A world can appear coherent while hiding deep instability. A category can feel precise while concealing the decisive mechanism. A single close flyby can feel like intimate knowledge while still leaving the largest questions unresolved. Neptune teaches all of that with unusual severity because everything about it encourages underestimation first. The distance encourages it. The elegance encourages it. Even the blue color encourages it. Yet once the world is followed seriously, none of those simplifications survive intact. What remains is something more demanding and more valuable. A planet that links visible weather to buried heat to pressured chemistry to electrical behavior to magnetic asymmetry to structural oddity to formation, history to moon capture, and all of it, to the wider question of how common Neptune-like worlds across the galaxy might actually work. That chain of consequence is Neptune's real grandeur. Not merely its size, not merely its winds, its connective force, the way every feature becomes a doorway into a larger layer. Neptune begins as a point in the dark and ends as a network of implications. It is a planet that enlarges itself through relation. That is why it matters even beyond science. Neptune shows with uncommon clarity what it means to confront a reality that is too distant for instinct, too complex for first categories, and too important to leave half understood. It forces patience. It demands inherited observation. It rewards discipline over flourish. It reminds us that the universe is not obligated to become simple at the edge of visibility. Sometimes the farther out one goes, the more obvious it becomes that the clean picture was only possible because the deeper machinery had not yet been seen. Neptune is one of those revelations. It stands at the boundary of the solar system and turns the boundary into a fraud. The edge is not empty. The edge is active, layered, violent, and unfinished. The darkness is not the absence of process. It is the concealment of process. The distance is not a reduction of meaning. It is an increase in the work required to earn meaning honestly. And that may be the final transformation of the opening image. Neptune no longer appears as the quiet blue giant waiting at the end of the planetary sequence. It appears as one of the places where human understanding is stretched into its proper shape, forced to trade neatness for depth and summary for system. The world that first looked serene now looks loaded with hidden motion. The world that first looked final now looks foundational. The world that first looked remote now looks central to the unfinished task of learning what planets really are. When light is weak, pressure is immense, history is violent, and appearances are least trustworthy. Neptune does not ask for admiration alone. It asks for return. It asks for better instruments, longer records, deeper models, and eventually another journey into its dark blue weather and strange surrounding system. Because the planet has already told us enough to know that the first picture was false, and not nearly enough to know what the full picture is. That is the last and most durable truth. Neptune remains one of the greatest unfinished worlds in the solar system, not because it has yielded too little to matter, but because it has yielded enough to prove that the real story is larger than the one we can yet hold. What Neptune finally changes is not just the map of the solar system, but the meaning of distance itself. It begins as a blue point so remote that the mind is tempted to compress it into a symbol, the last giant, the cold edge, the fading margin of sunlight. But the longer the planet is followed, the less it behaves like a symbol, and the more it behaves like a challenge. Distance does not empty Neptune of meaning. It concentrates meaning behind layers of difficulty. Weak light does not quiet the world. It makes its hidden energy more startling. A smooth blue face does not simplify the planet. It conceals the deeper architecture that gives rise to violent winds, unstable storms. Strange magnetism, pressured matter, and a history written in capture and disruption. That is why Neptune matters so much. Not because it is merely beautiful, though it is. Not because it is merely mysterious, though it remains that too. It matters because it forces a more mature idea of what a planet is. Not a colored sphere with a list of traits attached to it, but a system of linked depths, where atmosphere, heat, chemistry, structure, orbit, and history keep shaping one another across scales too large for instinct and too slow for impatience. In that sense, Neptune is not the quiet final planet waiting at the end of the story. It is one of the places where the story becomes hardest, richest, and most honest. A world still unfinished in our knowledge. A world still active in the dark. A world that turns remoteness into revelation and reminds us that some of the deepest truths in the solar system do not lie where sunlight is strongest, but where understanding has had to work the hardest to follow.